Okay, thank you. Yeah, I'm from Munich at a Technische University, doing currently my PhD there, and I want to talk to you about a statistic summarizing relative timing in trees. This has been joint work with, this was wrong, so this is the, okay, with Eric. It all started down in New Zealand at a great CAS workshop Mike organized, and while we were waiting for the train, we were thinking about tree statistics. And then, so that was here. And then Daniel Ford, he is a great statistician, so he helped us with the statistics. Yeah. So tree statistics, what is this all about? So with tree statistics, you can investigate the probabilities of reconstructed trees. So again, like in David's talk before, I'm assuming we have the about correct tree, so we don't care about the reconstruction, but then what can we say, seeing this reconstructed tree, what can we say about the process, the speciation process behind? And with the tree statistic, you summarize some characteristics of your tree. So you have your big tree, which is kind of a complex structure. You have this combinatorial structure and all the edge lengths and so on. And with a statistic, you summarize this tree in one number. So of course then you specialize on one certain aspect of the tree, and there are statistics around. So I guess the most important one, or the one most often used, is the Collet statistic, which summarizes information about the tree shape. So the Collet number, basically the statistic you get, is really low if you have a very balanced tree. So if your two subtrees and a big tree look kind of alike, and at each interior vertex, if you look down a tree, the two subtrees look alike. They would be very balanced and a very low Collet value, versus a very unbalanced tree, like in the extreme, the caterpillar tree would have a very high Collet statistic. And when David was saying earlier that most trees are too unbalanced, there were big studies with the Collet statistic looking at all the trees around, how balanced they are, and the typical value of Collet was way lower, way higher, more unbalanced than what you would expect under a pure chance model like the Yule model. Then the second statistic around, which is quite used, well, not as lot, but a lot, I guess, is the gamma statistic. And the gamma statistic summarizes the time between speciation events. So we throw away the information about the tree shape, the combinatorial structure of the tree, but we look at how much time was between the first and second speciation event, the second and third speciation event, and so on. And then from those values, we calculate one value, which is the gamma statistic. And the graphical representation is in lineage to time plots, which we also saw in the last talk. Okay, and then Eric and me were thinking, well, this is nice. We have a tree shape statistic, so just the combinatorial structure versus the timing information. But can we somehow combine this information? The motivation behind that was, look at this example tree. So it's pretty balanced, I guess. The subtree A and B have about the same size, and also all the subtrees in between, they're not, not too balanced, not too unbalanced. So under a pure chance model, we would expect quite a normal Collet value, nothing unnormal. And then the gamma statistic considers the timing between, no, I can't say that right, between the first and second speciation event, the second and third and fourth, and so on. And maybe we have here somewhat clustered speciation, but still it's, spread around time. It's not that all the speciation was at that point in time. But clearly, you probably say this is not typically under pure chance. All these speciation events in clade A were clustered together in this short period of time, versus in clade B, it's distributed well throughout the whole evolutionary process. So how can we summarize this information? How can we test if there was such a, we called it lineage-specific burst. So there was some burst here, we can clearly see, but how can we summarize that and put it in some statistical framework so that we can test if our tree actually shows some unnormal behavior with respect to this lineage-specific bursting. And for summarizing that, we need to introduce a so-called ranking of our speciation events. So ranking is simply we assign the most recent common ancestor. The first speciation event rank 1. The second speciation event, which is this one, has rank 2. The third speciation event here has rank 3, and so on. 4, 5, 6, here would be 7, and so on. And we say that a neutral model, like a pure chance model, each ranking would be equally likely. It wouldn't matter if we're, it would be distributed quite equally here and here. We would shuffle those speciation events on the left side and the right side about this, uniformly. And clearly here, that is not the case. And just a minor note, so this sounds now not like how neutrality normally is defined. Normally, I guess, neutral model would be the Yule model or constant rate burst dash process, but they're all included here. They are just stronger assumptions for neutrality, because there we would, in those Yule models, the Yule model and constant rate burst death, we have that each ranking plus tree shape is equally likely. But we only really want each ranking equally likely. So our statistic wouldn't be rejected just because we have one big subclade and a small subclade, so we are unbalanced. But we really look for those bursts. So how can we summarize this ranking information? Here's an example. There are two trees. Both have the same tree shape, but the interior vertices in this left tree, we have the first 4 speciation events in the right clade being before the left clade, so we code it with RRRRLL. And in the right side, the first speciation event on the left side was already a third, so we code it RRL, RRL. And under our neutral model, both these rankings conditioned on the tree shape are equally likely. And we call these sequences shuffles on a vertex. So we don't care about how the ordering is within a subtree, but just we look at the 2 subtrees below a vertex. So what does those shuffles have to do with the ranking? So each ranking equally likely, which are our neutral models, are actually equivalent to that at each vertex, each shuffle is equally likely. So if I'm in this vertex, this shuffle has the same probability as that shuffle. Then if I go down a tree and I'm in this vertex, each shuffle on that vertex, so on those 3 speciation events below, would be equally likely as well. And this holds because we have a one-to-one correspondence between rankings and shuffles on each vertex. So one ranking induces or corresponds to exactly one shuffle for each interior vertex. You can just write down the function basically. So then instead of summarizing all the ranking information, we want to summarize the shuffle information for each interior vertex. So how can we summarize this shuffle information? And we chose to use the run statistic. So the run statistic is nothing we came up, we just used it from statistics. It's a popular statistic, and what it does, it takes the number of, it takes a shuffle and it looks at the number of sequences with the same letter, and the number of sequences with the same letter would be the runs. So I guess an example, it becomes clear really quick. So 2-4 shuffle, 2 L's and 4 R's. For example, RRL, RRL has 4 runs because we have a sequence of 2 R's, that's the first run. Then we have 1 L, which is the second run, 2 R's is the third run, and an L is the fourth run. So this shuffle would have 4 runs. And in general, it is known from statistics that an MN run, so M L's and N R's, has the following distribution. So XMN would be the random variable for number of runs of an MN shuffle. Well, and we have to distinguish if this number is even, odd, or even, and we have a function of those binomials. So easy to calculate. But now we have a statistic for one single shuffle. we have the whole tree though. So we have n-1 interior vertices on a tree with n leaves, so we have n-1 shuffles, right? So we have to combine all those shuffles to one statistic. And the way we chose to combine all the shuffles for each interior vertices was that we simply sum up the number of runs at each interior vertex. So at each interior vertex we have a shuffle, we calculate the number of runs, and we just add that up over the whole tree. And the distribution for those runs in a tree can then be calculated recursively, actually. So the idea was for that, the number of runs in a tree T, so we have the tree T given, and the probability that a certain tree T, which looks like tree T with one subtree L and one subtree R, and L shall have, let's say, M leaves and R has N leaves. The probability that that tree has exactly K runs is the probability that, first of all, the MN shuffle, so the shuffle on that vertex, has, let's say, I runs, times the probability that in a left subtree, let's say we have J runs, and in the R subtree we have K minus I minus J runs. So overall we would have I plus J plus K minus I minus J, which equals K runs. We sum that up over all possible I's and J's and get a recursive formula for the probability distribution of the run statistic. And that's actually what we need for testing the hypothesis if our tree evolved under this class of neutral models that each rank function is equally likely. So if there's a burst of speciation, it was global. We didn't have lineage specific bursting. And yeah, we can calculate, once we know the distribution, we can calculate all the quantiles for our statistic and do appropriate testing. And that's what we actually did. So well, the first idea was actually we thought, oh, the statistic, it would be nice applying it like coalesce to the whole tree-based database or just a big database and see if the quantiles would be at 0.5 in average, so it would be uniform ranks or not. But the problem is that for our statistic, we actually need ultrametric trees, so the trees have to end all at the same time today, and we can't have, well, if they don't follow the molecular clock, we have a problem. So we could just look at certain special trees which followed the molecular clock or were ultrametric. So investigated a big tree of ants from Corey Moreau. And the lineage to time plot of their tree showed a substantial increase at some stage. So yeah, for some reason, speciation just started bursting basically. And the question of the authors was this a global, like, did all the lineages in the ant tree start speciating faster, or were there just some lineages, maybe just one lineage which decided for whatever reason to start speciating much, much faster than before? And we applied our test to this tree. And here you see this tree. Unfortunately, this tree goes on down here as well, and was quite big. But so actually, we only have to care really about the root, because that summarizes all the results. So the root, this 147 is just the label of the interior vertex. The 148 is the leaves below this vertex. So the whole tree had 148 leaves, and the quantile of our run statistic was actually 0.90, which means we would reject the hypothesis of a global burst versus a lineage-specific burst, well, let's say to a 5% error at 0.05. So clearly, there's no way why we would want to reject the hypothesis of a global burst and not lineage-specific. So there was no lineage-specific behavior within the tree. And the last number which this program just gives back is the quantile of the individual shuffle within the whole tree. So you can go into the tree and see, well, if you then zoom in, if some shuffles were quite unexpected, and also all the interior vertices have the quantile for the subtree. So for interior vertex, you could look at the subtree, just the leaves below this vertex. So this would be another root then, and you can look what the quantile of the run statistic for the subtree would be. But clearly in the whole tree, everything behaved quite normal and nicely. So the burst is just a global burst. So I don't know, the ants decided to speciate because of, I don't know, maybe it got warmer or colder. Or so some comments on that. First of all, we can not only test one single tree, but we can also take the posterior of Bayesian methods, for example, and test the whole posterior for neutrality. And this can be done either if you infer phylogenies or if you work within populations. And if you're within populations, one thing Eric wanted me to point out is that the population size is allowed to change arbitrary. So I guess that's something. So if you assume the correlation, and then our method doesn't care about if you have constant population size or exponential increasing population size, because those models always in those models then each rank functions is equally likely no matter how the population size behaves. And all those programs are available at my homepage, and they're coded up in a Python package CAS. This has some more features, but yeah, they documented in a README, and we just called it CAS because that was on this nice CAS workshop, and we couldn't think about a better name, so we thought CAS would say everything. And just to show you that it's really easy to use those programs, because I'm normally always scared if I see new, packages, and then I think, oh, maybe it's hard to get them run. So you just put into the command line Python stats.dat, and then the file with your new trees. They should be in UIC format. And as an output, you get this tree I showed you earlier. So again, in UIC format, there would be all the quantiles stored in this tree, and you get a separate file with the statistics summarized as well. Okay, and I want to end with saying thank you for your attention, and especially thanks to Mike Steele, you see him here, for very helpful comments on this whole project, and they're my two co-authors thinking hard about tree statistics. Thanks.
Questions?
When are ants around?
I don't know. I would have to look in their paper.
Does it include termites? Or there are no ants?
I have no idea, I have to admit.
So these runs tests tend to be really conservative, right? So how sensitive is it to tree size and things like that? I would imagine that if your trees are small, you probably can't get
Yeah, that's right. So if the trees are too small, you don't get any reasonable answers. So my feeling was like you should have at least, let's say, maybe 50 leaves in that range. So from then on, it seems to be quite reasonable. But if you have a tree only on, let's say, 10 leaves, it's too, there could be, some artifacts are too likely, basically, that it won't work. You have to have bigger trees.
Something I wasn't quite clear about. So once a branching event has happened, let's say it happens in the left subtree, you've now got two lineages in that left subtree, and only one in the right subtree. So it seems like you should have more opportunity for another branching event to happen in the left subtree. Are you taking care of that because you're summing over all the vertices, or does it not being IID not matter?
No, so I assume that I have my tree shape, and then I just consider all the possibilities for a ranking, and then I just say each of those ranks is equally likely. So if there was much more happening, let's say on the left side, of course there there's a different number of possible rankings than if it would be really balanced. But I just take into account those rankings which are actually possible, and then each of them should be equal likely. And if you assume on top that, you know, like something like Joule or so, then also your shape would be equally likely. But
Right, let's thank the speaker again.